Hello student, in this lecture I will discuss another example. So see the example. The question is, the open loop transfer function of a control system is given by GSHS equal to k divided by s into s plus 6 plus into s square plus 4s plus 13. Sketch the root locus and determine the breakout point, the angle of departure from complex pole and the stability condition. Okay, so now let's see the solution. So see here in our system there are 4 open loop poles, that means P equal to 4, and poles are 0, minus 6, minus 2 plus J3 and minus 2 minus J3. And the number of open loop zeros Z equal to 0. Now see the number of root locus branches N equal to P, okay, because here P greater than Z, okay, and therefore number of branches is 4 because in our system there are 4 open loop poles. And on the real axis the root locus lies between two poles s equal to 0 and s equal to minus 6. Okay, so now we put this pole on our graph. Okay, so see here put the pole, mark the pole in our graph. Okay, so this is our real axis and this is our imaginary axis. Okay, and our system have 4 pole. One pole is this 0, s equal to 0, another pole is s equal to minus 6, and another pole is minus 2 plus J3, and another one is minus 2 minus J3. There are 4 pole. Okay, now identify the portion of the root locus. Okay, so how we will identify the portion of the root locus? We take a point on the real axis, like here we take the point minus 6, s equal to minus 6, and see the right side of that point. So if we consider the point minus 6 and see the right side, then we find only one pole is there, that is odd number. No one, there are 3 pole is there. Okay, that means this is odd number. Okay, that's why this whole portion, that means in between 0 to minus 6, this whole part is the region of root locus. Okay, that's why here I have mentioned on the real axis the root locus lies between two poles 0 and s equal to minus 6. Now let me clear these things. Now we find the angle of asymptote. So the angle of asymptote is found by this equation 2k plus 1 into 180 degree p minus z, and k varies from 0, 1 to p minus z minus 1. Okay, so here if we put the value of p and z, then this is 3. So the values of k are 0, 1 to 3. Okay, now we find the angles of asymptote. The angles of asymptote are 45 degree. If we put the value of k, there are 4 value of k. So if we put the 4 value of k, then the angle of 4 asymptote are 45 degree, 135 degree, 225 degree and 315 degree. Okay. Now we calculate the centroid. Because we draw the asymptote on the root locus plot. So root locus intersect at a point on the real axis, which is called centroid. So for that we calculate centroid. Okay, so using this equation we calculate centroid. That means centroid, here I have mentioned x, and this x equal to sum of pole minus sum of 0, and this divided by p minus z. Here we consider only real part of poles and real part of 0. So here if we consider only real part of pole, then the sum of pole is minus 10. Okay, and in our system 0 is 0. Okay, and in the denominator p equal to 4 and z equal to 0. So our centroid is minus 2.5. Okay, So now put the centroid on the root locus plot or on the graph and draw the asymptote. So see, our centroid is minus 2.5. So where is 2.5? So this is our 2.5 minus 2.5. So from this point we draw the asymptote by angle 45 degree, 135 degree, 225 degree and 315 degree. So this is our 45 degree angle. This is our 135 degree angle. This is our 225 degree angle. And this is our 315 degree angle. Okay, clear? Now let me clear this thing. So see, here we have 4 poles. Okay, so from this 4 pole, 4 branches starts. Okay, so from 0, 1 branch start. First pole is 0 is equal to 0. From 0, 1 branches start in this way. For 6 is equal to minus 6, 1 branch start in this way, because the root locus portion is in between 0 to minus 6. That's why from minus 6 locus start in this direction and 0 locus start in this direction. Okay, but we don't know from this pole and from this pole how locus start. Okay, now see here 2 adjacent poles are there, 0 or minus 6, and from 0 locus start in this way and from minus 6 locus start in this way. Okay, so obviously in this case we will find breakaway point. Okay, so for finding breakaway point we need to find characteristics equation. Okay, now see the characteristics equation. So we basically know the characteristics equation is 1 plus GS HS equal to 0. Okay, so here put the value of GS HS. So after putting the value of GS HS, the characteristics equation is this: S into S plus 6 into S square plus 4S plus 13 plus K equal to 0. So here from this equation you find K equal to minus S to the power 4 plus 10 S cube plus 37 S square plus 78 S. Okay, so for finding breakaway point we need to calculate dk ds. So here we differentiate K with respect to S and put the differentiation dk ds equal to 0. Okay, so if we differentiate K with respect to S, then our differentiation is minus 4s cube plus 30s square plus 74s plus 78, and this is equal to 0. So from this equation we find S, the value of S. Okay, so value of S by calculator. Okay, so we by calculator we calculate the value of S equal to minus 4.2. So at minus 4.2 it satisfies the condition. Now we put this 4.2 in our graph. Mark this 4.2 in our graph. Okay, so see, this is our 4.2. Okay, clear? This is our breakaway point. Now see here we have 2 complex poles, then that's why we need to calculate angle of departure. Okay, so we have already known the equation to find angle of departure. So angle of departure, the equation of angle of departure, phi d means angle of departure equal to 180 degree minus phi p minus phi z. That means sum of phi p, sum of phi z. Okay, now see here the angle of departure from the -2 plus J3. So first we consider this complex pole -2 plus J3. So for this pole we calculate angle of departure. So for this pole we calculate the angle of departure by this equation. Phi -2 plus J3, 180 degree minus 5P1 plus 5P2 plus 5P3. Okay, here there is no phi z because in our case there is no 0, that means this is 0. Okay, now we find 5P1, 5P2 and 5P3. Okay, let me clear these things. Now see how we will find 5P1, 5P2, 5P3. Okay, so see the figure here. See, this is our one pole s equal to 0. This is our another pole s equal to -6. This is our third pole and this is our fourth pole. Okay, now we calculate 5P1, 5P2, 5P3. Okay, so we consider this complex pole. Okay, so what is 5P1? 5P1 is the angle between first pole, that means s equal to 0, this is our first pole, the angle between this pole and this pole, that means this is our 5P1. What is 5P2? The angle between this pole, means here we consider this pole, so the angle create this pole and this pole, this is our 5P2. And what is 5P3? The angle between this pole and this pole. Okay, this is our 5P3. Okay, see, this is our 5P1, this is our 5P2 and this is our 5P3. Okay, so how we calculate 5P1? So 5P1 is basically 180 degree minus this angle. So this angle is nothing but tan inverse 3/2. So 5P1 is equal to 180 degree minus tan inverse 3/2. That means 123.6 degree. Okay, now we calculate 5P2. 5P2 is this. So 5P2 is equal to tan inverse 3/4. That means 36.86 degree. Okay, so this is our 5P2. Okay, and 5P3 is this and this is our 90 degree. Okay, so here I have mentioned 5P3 90 degree. Now put the value of 5P1, 5P2, 5P3 in this equation. So if we put the value of 5P1, 5P2, 5P3 in this equation, then our phi for pole -2 plus J3 is this -70.46 degree. Okay, and in the same way we find the angle of departure for next another complex pole is -2 minus J3, and this is obviously plus 70.46 degree. Okay, because they are complex conjugate pole. Okay, so if we calculate one angle of departure for one complex pole, then we easily calculate the angle of departure for another complex pole. Okay, clear? Now we put this angle in our graph. Okay, so see here we know there are 4 poles. Okay, pole are 0, 0, -6, 0, -6, -2 plus J3 and -2 minus J3. Okay, and each pole root locus start. Okay, so there are 4 poles, that means from 4 pole 4 locus start, and we know the portion of the root locus is this 0 to -6. Okay, that means from 0 locus start in this way and -6 locus start in this way. Okay, and our breakaway point is this -4.2, and our centroid is this -2.5. Okay, now see how locus move. Okay, now let me clear this thing. So see, from -6 locus start in this way, and from 0 locus start in this way, and they meet at 4.2. This is our breakaway point. So from this breakaway point, from at -4.2 they meet each other, and from this is our breakaway point, and from this breakaway point locus leave the real axis in this direction. Okay, and see the locus follow the asymptote. This is our asymptote. Okay, clear? This is our asymptote. This is okay, follow in this way. So from 0 and -6 locus start in this way, and they meet at -4.2, and from -4.2 they leave the real axis and follow the asymptote in this way. Okay, and we have another 2 pole. One is -2 plus J3 and another is -2 minus J3. So see, from -2 plus J3 locus start in this way at angle -70.46. That means angle of departure at -2 plus J3. When okay, so from -2 plus J3 locus start in this way and follow the asymptote in this way, and -2 minus J3 locus start in this way at angle plus 70.4 and follow in this way. Okay, clear? This is 9. This is 90 and this is plus 70.4 degree, and from -2 plus J3 is angle of departure is -70.46. That means this is our plus 90 and this is our -90. So in this way locus start at angle -70.4 and follow the asymptote. Okay, clear? So we have 4 root locus branches and they move in this way. Okay, so let me clear the highlight portion and see the whole diagram. Okay, so see, from 0 and -6 locus start and they meet -4.2. This is our breakaway point, and from 4.2 from 4.2 they leave the real axis and move in this way and follow the asymptote and go at k equal to infinity. Okay, because there in our system there is no 0, that's why locus go at infinity. Okay, and from our complex pole locus start at angle from, if we consider -2 plus J3, then locus start at angle -70.4 degree and 4 degree and move in this way and go k equal to infinity plus infinity. And if we consider -2 minus J3, then locus start at angle 70.46 and move in this way and follow the asymptote. Clear? Now see, let me clear this portion. Now see this locus cut the imaginary axis. This locus cut the imaginary axis in this point. So how we calculate the point? Okay, so for this we use to calculate this point, we use Routh array. Okay, now see. Now see, the Routh array, from characteristics equation we calculate the Routh table or Routh array. We have already known, we have already discussed in Routh stability criteria. So from characteristics equation we made this Routh array. Okay. Now see, the intersection of the root locus plot with the imaginary axis is given by the value of k obtained by solving following equation. That means we find the value of k. So for value of k, we calculate this equation, 78 minus 0.34k equal to 0. Okay, and this equation we calculate k equal to 229.4. Okay, so the intersection point is determined by solving auxiliary equation for s square term. Okay, so here auxiliary equation means the above row of this equation, that means 78 minus 0.34k. We consider this, that's why auxiliary equation is its above row. Okay, so the intersection point is determined by solving auxiliary equation for s square term is 29.2 s square plus k equal to 0. Okay, and here we put the value of k 229.4 equal to 229.4. So from this equation we calculate s equal to plus minus 2.98 j. That means this intersection point is plus 2.98 j and this intersection point is minus 2.98 j. Okay, so this is our complete root locus plot of our system GSHS equal to k divided by s into s plus 6 into s square plus 4s plus 13. Okay, so here need to find the stability condition. Okay, so from the root locus plot, so from this plot it is noted that for k greater than 229.4 the two roots have positive real part. Okay, so see, from the root locus it is observed that for k greater than 229.4 the roots have positive real part. Therefore the system is stable if k less than 229.4. Okay, so this is our stability condition for taken system. Okay, thank you.